Okay. Okay, so it's the last lecture. And what I'm going to do in this lecture is, let me just open the chat in case anyone writes anything in the chat. Wait. Yeah. Okay. And okay, so what I'm going to do in this lecture is I'm going to finish talking about convergence of Fourier series. And then I'm going to talk about an important other operation you can do on Fourier series, which somebody hinted at the last lecture, which is differentiation of Fourier series. And this is really important in the application of Fourier series to partial differential equations, which we won't actually be covering in the course, but you can read about it in the textbook if you want, and it'll come in handy if you do it later. And then I'll tell you about some cool applications of Fourier series. It's really one of the most useful things in math, and hopefully you'll see why. And then I will tell you a few minor extensions of this Fourier series on the interval minus pi to pi. This is the content of section 10.4. This will just take like 5 minutes. And then I'll briefly review differential equations. So most of the material we've covered after the second midterm. I'll review it on one slide just to try to make it a little more cohesive. So okay, so what did we do last time? So last time we defined this vector space V pi of functions from the interval minus pi to pi to r, such that both the function and its derivative are piecewise continuous. So that means you're allowed to ignore a finite number of points, and apart from those points, it should be both these functions should exist and they should be continuous. And there's one more condition which is bounded, which I didn't write in the last lecture, but that's important. I don't want the function to go to infinity or something. So that's a vector space. Somebody's asking if we'll have review lectures next week. We won't have review lectures. I'll have extra office hours and stuff like that, but we won't have a separate review lecture. Although you may have them in discussion. Okay, so we have this vector space, and then we turned it into an inner product space by defining this inner product, which was an integral. And this was a generalization of the dot product, and maybe I should have mentioned earlier, it even looks like a dot product, right? It looks like an infinite version of just, what if you had a finite set of points and just did this, right? That would be a dot, that would be something like a dot product. Well, this is just an integral instead of. And then, using this, we got all these concepts of orthogonality and so on, and we concluded that this following set. So if you look at all of the cosine functions, where n is a non-negative integer, union all of the sine functions, where n is a positive integer, these form an orthogonal set in this inner product space V pi. We did that little calculation. And then we defined this thing called the Fourier series, which was inspired by, what would the formula for expanding some other function in V pi in this orthonormal basis be? We defined the Fourier series of a function f to be the following series. Okay, where these coefficients were defined using some integrals, which were actually just inner products. So the reason for this 2 was so you could have a convenient formula for all the ANs that work, all of them, including A0. Okay, so this is a series whose coefficients are defined using integrals of f. Okay, by the way, these are very important numbers. They're often called the Fourier coefficients. And this is actually quite different from Taylor series, right? Because in Taylor series, how do you get the coefficients of the series? You take derivatives. It's actually doing the opposite. It's the coefficients you get them by defining integrals. And then we proved this. We didn't prove actually at all. We stated an important theorem called the Convergence Theorem for Fourier series. I mean, there are many, but this is one. This is theorem 2 in the book. And what it says is, well, if you have a function in V pi, then two things happen. The Fourier series all converges for every x. Okay, so maybe I'll draw. That's not obvious, right? It's an infinite series with sines and cosines. Whenever you have an infinite series, the first question you should ask is, does it converge? And for which x does it converge? So first of all, it converges. And it's basically equal to the function. So it's equal to the function if f is continuous at x, which just means if the left limit is equal to the right limit. Otherwise, it's the next best thing. It's the average of the left and right limits. And both of these only apply for x in the interior of the interval. And at the endpoints, you have to do something similar to this left and right limits. You have to take the upper limit of minus pi and the lower limit of pi. I'll explain in a moment why this is natural. Okay. So, I mean, what this essentially says is that the sines and cosines are the orthogonal basis for this inner product space V pi. That you can expand any function as an infinite series in cosines and sines, where the coefficients are given by these inner products, modulo this minor caveat, right? That if you have points that are discontinuous, then you have this thing that's slightly more complicated than being equal. Okay, so only difference from the Fourier series literally being equal to the function. So somebody asked, what do you do if the interval isn't minus pi to pi? I'll talk about that later. Right now, let's just focus on minus pi to pi. All the key ideas are in the interval minus pi to pi. Okay, so that's the convergence theorem. So any questions about the statement of the convergence theorem?
So that means when, for example, when your x is equal to pi, that so the convergence result on x equal to pi is basically the right limit of minus pi plus the left limit of pi over 2.
No, it's the left. It's the right limit of minus pi plus the left limit of pi. That's correct. Divided by 2. Yeah, both terms are divided by 2. Yeah, if that isn't clear, both terms are divided by 2. Everything is real. Everything is real. Somebody asked real. Okay. So
does A and Bn come from the inner product?
Yeah. So another way to write these integrals is as inner products, right? Let me just write them. Right. This is, at least when n is, I mean, there's a 2 when n is equal to 1. This is literally this, right? This is literally this. So okay. I mean, the convergence theorem has a few little technicalities, but they're really they're important, but ignoring them for the moment, the theorem is really just saying this is exactly what you would get if you had an infinite orthonormal basis, right? So
Okay.
Apart from what it's saying is you really have this picture, right? You have these two orthogonal subspaces of even and odd functions. And in here, you have the sines. In here, you have the cosines. And you really have this expansion that any f is equal to what you would get, right? So the one function inner product f over the squared norm of the one function times the one function plus summation over all n cosine and x f over norm squared of cosine and x cosine and x plus the sum over the sines. Okay, just like in chapter 6. Somebody's asking, why is it the average of left and right limits at discontinuity? We unfortunately can't prove that. You'll have to take, I think, math, I don't know, 104, maybe 105 for that.
So I also wanted to ask, why, when x is equal to pi or negative pi, why you choose pi and negative pi? Because when you say this is
to say a little bit more about, although we won't be able to prove the convergence theorem, it's not easy to prove, and you'll prove it maybe later in other courses. I'll explain why it's natural to take the limit of the average of the upper limit for minus pi and the lower limit for pi, though. Okay. Okay, and we looked at one example. The example was this step function. Sorry, 0. Let me just write it in interval notation. And we calculated the Fourier series of that step function last time. And what did we calculate? Well, we calculated that the ANs are 0, and that's just because the function is odd, so the cosine coefficients are 0. And the BNs are 4 over n pi. And so the conclusion was that the Fourier series of this function s is therefore the series 4 over pi times sine x over 1 plus sine 3x over 3 plus sine 5x over 5. So, okay, and this may be the first time you've seen a series like that. And the theorem says that that series converges. Okay, so that's not obvious, but it says that it converges for every x in the interval. Now, this function, if you plot this function, it looks like this, right? So let's say, so this is minus pi, this is pi, and this is 0, right? So the function has one discontinuity at 0. So the theorem says that the series converges for every x in the interval. Equal to 1, sorry, not x, for x in 0 to pi, excluding the endpoint. A little dirty. Equal to -1 for x in minus pi to 0. And at 0, it should be at 0. So let's see. So what should it be at 0? Yeah, anybody know what it should be at 0 according to the theorem?
Should be 0, correct?
It should be 0. The limit of, right? So if you take the left and right limits of this function at 0, the average is 0. So it should be 0. And what should it be at the endpoints?
Well, that should be 1 or -1, right? But like if you take this, the formula, you get 0.
Yeah, so it won't be 1 or -1. According to the formula, it will be also 0 because you will take the right limit of minus pi and the left limit of pi. And if you average those, you will also get 0. So the theorem says that the Fourier series at minus pi or plus or minus pi equals 0, right? Now,
Like,
so that's what the theorem says. And that's actually true, right? So you can check these easily, right? So let's check these. So the series is a bunch of sines, right? What's sine of 0? It's 0.
0.
Right? Okay.
Sine of pi is also 0.
Sine of pi is also 0, right? So it checks out. Okay. So that's what the convergence theorem says. But I mean, the really amazing thing though is that this is some crazy looking bunch of trigonometric functions, right? But if you plug in any number that's not 0 or pi, you always get 1 or -1. And it sharply moves from 1 to -1 as you change the sign. So there's some crazy cancellations going on in the series. So what I want to now do is show you a picture of this. Okay, so this is a calculation and I'm claiming it's true. I'll show you a picture that will at least make you imagine why something like this could be true. Now to show you the picture, I'm going to use something that's called a periodic extension. A function, say g to r is periodic, or let's say 2 pi periodic, if what you think is true, if it repeats after every 2 pi. If g of x plus 2 pi equals g of x for all x in R. So this is now a function on the whole real line. So anybody know 2 pi periodic function?
Like sine.
Sine. Yeah. Sine
Cosine.
is sine. Cosine x, sine x. Okay, somebody said the function 4, that's correct. Any constant function is also periodic. Could also have cosine 3x. any integer multiple would also be periodic. And so
Tangent?
tangent is actually not defined on all of R, right? So that's a problem. Tangent blows up.
Sine times cosine?
Sine times cosine, yeah. Sine times cosine. Now what we're gonna do is so far we've been doing everything on this interval minus pi to pi with Fourier series. We're now just gonna do something that's fairly trivial, but an important change in viewpoint, which is if you give me a function on minus pi to pi, I can just repeat it every 2 pi intervals and create a periodic function. Right? So given function f of minus pi to pi satisfying f of minus pi equals f of pi. So that means, let's say I'm given some function. We'll look at this function in a moment. Suppose I'm given a function that looks like this, so minus pi to pi. And at minus pi and pi, it has the same value. It's a periodic extension. Let's call it fx, which is now a function from R to R, is defined by f of x plus 2 pi equals f of x. So what I mean, all that's saying is, if you give me some x in the interval, I know what to do. If you give me some other x out here, well, I'm just going to add 2 pi until I end up in this interval and take that value. So all that literally means is I just copy this thing forever. Okay. So really I'm saying it's uniquely defined by. Is uniquely defined by this, and f of x equals f of x for all x in R, and f on the interval, it's just equal to f of x. Okay. So what I can do is, for any function on the interval, maybe by changing the value at one point in order to satisfy this endpoint condition, I could make it periodic, right? And now the Fourier series theorem can be reinterpreted as saying, if you have a periodic function, then the Fourier series converges on all of R, and f of s is equal to f on all of R. So one consequence of the is that if f is 2 pi periodic, and continuous, and f prime is piecewise continuous on this interval. So that means the piece of f sitting on the interval lies in T pi. Then literally it's equal to its Fourier series. Okay, because then none of those discontinuity cases occur. So actually, okay, the thing I'm about to show you doesn't exactly apply to this. The thing I'm going to show you is what happens if you literally plot this example, the example of s of x, the step function. So this is telling you that the step function is an infinite sum of sines and cosines, right? So what I'm going to show you is how you can actually add sines and cosines to get something that looks like this. Somebody's asking, f doesn't have to be even to make the extension. No, f does not have to be even. Okay, this is a different. We'll talk about other extensions later where it does have to be even. This is just a 2 pi extension. I'm just repeating the whole interval. Okay, so watch this. So this is a cool video. Okay, so this is, so what is this? So this is going to be the function that we saw, the square wave. That's called a square wave, the step function. And I'm going to approximate it by sines, right? We saw that the Fourier series only had sines in it, right? So let's see how that works. So this is a sine. That's a sine function, right? If you move around a circle and plot the y-axis, you get a sine. Now, what if I add a sine 2x, a sine 3x to it? So what does that mean? That's like a little circle that's spinning faster, right? Now you add a sine 5x. Okay, so that's just 3 terms. Now you're at a sine 7x. Okay, so this animation is showing you what happens if you literally superimpose all of those. And you can see it's looking close to a square wave, right? The function that we had. Okay, so that's the meaning of this Fourier series theorem. That you can take something that really doesn't look like a sine and cosine, but if you add up exactly the right multiples of sine and cosine, so notice that the radii of these circles are also decreasing, right? Those are the Fourier coefficients, right? Because it was sine x plus sine 3x divided by 3 plus sine 5x divided by 5. And you have to get these radii exactly right to get this shape. So any questions about this animation?
For some reason, it reminds me of cycloids from Mass 53.
Yeah, it's probably related. I don't remember what cycloid is, but it's probably related. Okay, so I mean, there's a ton of animations on the internet. You can do this for various functions, and it looks pretty cool. Somebody asked, it can never be perfectly square, right? Slightly rounded at the corners. Yes, that's correct, because anything we actually plot is only going to be a few finite terms of the series, right? We're never actually going to be able to take an infinite sum, right? You can't actually do anything infinite in real life, right? So any finite, I mean, so what this means is, if you look at this infinite sum over here, right? So the key is this Fourier series. That's an infinite sum. If you take any finite sum of them, it's always going to be curved, right? Because it's a sum of sines. It won't be perfectly square. What the theorem is saying is that this converges to the square. So it's saying at all of the points except 0, it's going to get very close as you want to the right value. Any other question? Okay. Okay, so now, so this periodic extension, this is, I mean, this is a different way of even, some people even start the whole subject of Fourier series by only looking at periodic functions. And if you look at periodic functions, then it kind of makes sense why you have this, this condition for the endpoint discontinuities. Because if you take the periodic extension of a function, right, then, you know, at the endpoints, I mean, it's just at any other point, right? It's like there is continuity at any other point when you look at the extension. And when you approach it from the left and right, well, you're actually using the upper limit of minus pi and the lower limit of pi. That's why that shows up in the theorem. That's why it's natural. Because you can really view all of this stuff as a theorem about periodic functions. So does that make sense? Okay, I mean, it's a matter of preference. So I prefer to think of it first in terms of things on the interval minus pi to pi. Some people prefer to always think of Fourier series in terms of periodic functions. They're both equivalent, right? Periodic functions and functions on the interval minus pi to pi are one and the same thing, as long as you just make sure you identify the endpoints. The endpoints have the same value. Let me think. Could I say that once more? Yes. So what I'm saying is that this arrow indicates the upper limit of minus pi, right? But this arrow is also the upper limit of minus pi, right? But for the periodic function, that's the same as the upper limit of pi, whereas this is the lower limit of pi. So that explains why you would take the upper limit of the lower endpoint of the interval and a lower limit of the upper endpoint. Somebody had another question. Since it repeats the length of the line, is the length of the line that you can approximate have a maximum length? Yeah. So since it repeats, you cannot have a line that's longer than 2 pi, right? Unless the whole thing is constant. Right, so everything I've done is for 2 pi periodic functions. So I've written it here, right? So 2 pi periodic. So it repeats every 2 pi. So you cannot have like a square wave that has a length bigger than 2 pi in this setup. I'll talk about how to do longer ones later. There's an easy fix. It's a good question. Any other question? In the video animation, those blocks were in multiples of pi, but not every function does that. Yeah, not every function does that. As long as the function repeats every 2 pi, this will work, right? And I think the point is any function on the interval, any crazy weird function on the interval, if you just repeat it a bunch of times, it'll become a periodic function. Right? So, I mean, every function on the interval minus pi to pi, as long as it has the same value on the endpoints, can be turned into a periodic function. Does that answer the question? What if it's 3 periodic? Okay, everybody's getting to this question. What if it's 3 periodic? Okay, I may as well answer it now since many people asked this question. So let's answer this question now. Okay. So let me just make a remark. Okay, a function. So let me do the whole thing again. So remark if f. So let's define a vector space VL to be functions from minus L to R such that f and f prime are piecewise continuous and bounded. Okay, so now L equals pi is the case that we looked at earlier, right? So can you do the same thing as before? Yes. So the same thing works, but using the following functions: sine n pi x over L and cosine n pi x. Okay? And just the one. So this is not a big deal. If you give me a function is 2L periodic if f of x equals f 2L for all x in R. Everything works the same way. So see, these functions now, these are 2L periodic. You can check, right? I just scaled everything by L over pi. Yeah, okay, so I should say this says bounded. It says BDD, which means bounded. So you don't want this thing to go to infinity, otherwise the integrals could diverge or something. Okay? So there's actually a very cheap, easy way to fix this issue of what if it's not 2 pi periodic? What if it's 2 periodic? What if it's 1 periodic? Well, you just scale everything. Okay, so there's nothing new conceptually going on in that case. Does that answer the question? Everything works the same way. Same way, you just scale the trigonometric function. Big deal. Okay. So that's the convergence theorem. I want to show you one more example. Let's consider the function absolute value of x on the interval minus 5. Okay. What does it look like? So whenever you do Fourier series, just draw the function. That'll at least tell you whether it's even or odd. Pi minus pi. We actually drew its periodic extension right here. What's its Fourier series? So, well, this is an even function, so the bn are just going to be 0 because it's an even function, right? Sine is an odd function. And the ans, let's calculate them. Well, there's a formula for them. Right? So the integral is going to look a little different when n is 0 and when it's not. So when it's 0, so there are going to be 2 cases. So if n equals 0, a0 is just integral of absolute value of x dx from minus pi to pi, 1 over pi. And okay, we all know how to do that. That's 2 over pi integral of x dx from 0 to pi, which is 2 over pi times pi squared over 2 is just pi. So that was easy. Let's now calculate the other Fourier coefficients. Well, an is going to be 1 over pi. Again, this is an even function, right? Both cosine nx and x are even, absolute value of x are even functions. So this is going to be twice the integral from 0 to pi. So I can always do this trick for even functions of just x cosine. Yeah. Right, because on the negative interval, I mean, the integral on the negative half is the same as it is on the positive half. That's what one of the consequences of being an even function. Okay. Any questions about this first step? Okay, there's like math 1A or 1B or whatever. Okay, so now you actually need to compute this integral. Does anybody know how to compute this integral?
Use integration by parts.
Use integration by parts. So this is something that comes up a lot in Fourier series, integration by parts. Yeah, I know, cry a little. I don't personally like doing it either, but these ones aren't bad actually because they're just trig functions and polynomials. So how do you do integration by parts? Well, okay, so you do this times integral of the second one, so you get sine and x over n. You have some limits. So you have 2 over pi times. Yeah, Wolfram alpha also. Okay. Although doing this will actually show you something interesting about the coefficients I'll comment on. Minus integral of 1 times sine nx over n dx 0 to pi. That's what happens if you do integration by parts here. Okay, so the first term is actually 0. So why is it 0?
It's because of the sine, correct?
Yeah, because of the sine. Sine n pi is 0. So only the second term survives. And then if you integrate that, well, that's not that bad. You get that this is 2 over pi times, okay, so let's pull out the minus sign. What's the integral of sine nx? It's, I guess, minus cosine nx, but now you have an n squared here. And now you have a pi and 0. Okay. So this is minus 2 over pi n squared. Let's pull this out. You get minus cosine nx plus cosine 0. Right? And now, what is cosine nx? I'm sorry, cosine n pi. What am I saying? So what is cosine n pi? Well, it depends on what n is, right? So if n is even, cosine n pi is just 1, yeah. And if n is odd, it's minus 1. So this is minus 2 over pi n squared. You get a minus 1 to the n plus 1. Okay, that's a little funny. I mean, let's just cancel the minus. Well, yeah, no, let's just leave it that way. So if you have n even, you're going to get 0, and if you have n odd, you're going to get a 2 over there, right? So this is minus 4 over pi n squared, or n odd, else 0. Okay, so this happens a lot. Calculating Fourier coefficients, you need to do some integrals, often a little bit of integration by parts. So what's the conclusion? Well, the conclusion is that the Fourier series of this absolute value function is equal to so a naught over 2, so pi over 2 minus 4 over pi times a bunch of cosines, right? So cosine x over 1 squared plus cosine 3x over 3 squared plus cosine 5x over 5 squared. And by the convergence theorem, so this function doesn't have any discontinuities, right? And actually the values at the two endpoints are the same. So this is literally equal to absolute value of x. Okay, so this is quite amazing. You can write the absolute value function as an infinite sum of cosines with pi over 2 in the front. So any questions about this computation?
Did you choose n equals 1 for the final equation?
You mean here?
No, the final step.
No, so the conclusion was the conclusion of the calculation was this, right?
Yeah.
Minus 4 over pi n squared when n is odd. So what I've done here is I've just plugged in all the odd numbers.
Oh, I see. Okay.
I'm just plugging in all the odd numbers.
Right. Okay. Thank you.
Any other question about this calculation?
What happened to the left half of the absolute value of x
It's still
function?
there. It's still there. It just got sucked into this 2 over here, right? In the integral. I mean, it's here,
Oh,
right?
okay.
Yeah. So I use the fact that,
Okay.
you know, because it's even, this integral is equal to this integral.
Okay.
It's an even function, so the integral on the right half is equal to the integral on the left half, so the integral on the whole thing is twice the integral on the right half. Okay?
Wait, why is it only for odd number?
Ah, well, you have to do a little calculation here, right? So if n is even, then what's -1 to the even? It's 1, right? You get -1 plus 1 equals 0. Does that make sense?
Okay, I see now. Thank you.
Okay. So now let's try to relate the two examples. We have two different Fourier series, right? Let's write them together. The first is you have this step function, and the Fourier series of the step function was this 4 over pi sine x over 1 plus sine 3x over 3 sine 5x over 5. And then you had this other function, the absolute value function, and its Fourier series was 2 over pi minus 4 over pi cosine x over 1 squared plus cosine 3x 3 squared 5x 5 squared. So somebody asked this question that, well, you know, I just said that this is equal to absolute value of x, right? And somebody asked, well, what if you differentiate both things, right? The right hand side absolute value does not have a derivative at 0, whereas the Fourier series, I mean, each term of it does, right? So how could that possibly be? What does this, you know, what's the resolution here? How can this be right?
So you have this like f d of fx, absolute value of x over dx is basically f ssx. The reason I think is just because the slope of the function is just the slope of the second function is just like the first function.
Yeah. Okay. So I think what you're saying is you're making this observation that if you take the first series and literally differentiate every term, you literally get the second series, right? So because
Yes.
what's the derivative of cosine? It's just minus sine times n. So that cancels the thing in the denominator. This is literally equal to, you know, 4 over pi times, you know, sine, like 1 sine x over 1 squared plus 3 sine 3x over 3 squared plus 5 sine 5x over 5 squared. And these cancel, so this is literally equal to the Fourier series of the step function. Okay.
Mm-hmm.
So This is actually a theorem, which I'll now state. So it's called the differentiation theorem. This is theorem 4 in the textbook. What it says is that if f is 2 pi periodic, or equivalently, f of minus pi equals f of pi, as we saw, those are one and the same thing, and f prime and f double prime are piecewise continuous on minus pi pi, equivalently, f prime lies in v pi, and the Fourier series of f is then the Fourier series of f prime, where again, f prime is allowed to ignore a finite number of points. Everything is piecewise continuous. So this means you can ignore a finite number of points. Then the Fourier series of the derivative is what you would get if you differentiate term by term. Okay. So this theorem explains why this is happening, right? In our case, this function is not differentiable, but it is piecewise differentiable, right? If you ignore that one point, this is piecewise differentiable, and also it's so are its derivatives, right? If you ignore the one point, then its derivative is the step function, and you can differentiate that again if you ignore the one point. And it is 2-point periodic plus the. So by what I mean by that is you can make an extension out of it. Okay. Then what this is saying is you don't have to compute the Fourier series all over again. You can just take the Fourier series of the old function and differentiate all the terms, and you get the Fourier series of the new function. Okay. So one way people say this is, this means you can term-wise differentiate Fourier series. Under these conditions. Yeah, okay. So there's a discussion happening about why this is equivalent. What I mean is this condition f of minus pi equals pi means you can take periodic extension. Okay. If you have the same value at the endpoints, then you can view it as a function on R by copying it many. Does that make sense? So what this is saying is that this is not an accident. If you have these conditions, which are important, I mean, this doesn't work if it's not periodic, then you can get the Fourier series of the derivative, but now derivative is defined in a slightly different way, right? Which is you can ignore a finite number of points. Okay. So I'm not claiming that this, I'm not suddenly claiming that the absolute value function can be differentiated at 0. I'm not claiming that. I'm just saying that wherever it can be differentiated, this series will give you the right derivative. And importantly, what I'm not saying is, I'm not saying you cannot, I'm not saying you can't differentiate this identity term by term. Right? I'm not claiming that you can that you know d by dx of absolute value of x is equal to this everywhere on the interval. Right? There's nothing in this that says that. I haven't defined. I'm not. I mean, okay. If you take actually later on in like graduate math and so on, this is how you can define a derivative of a function that's not differentiable. But for now, we're not doing that. Okay. So, any questions about this?
So it's like, for example, if it is not periodic, then
Yeah, this doesn't work if it's not periodic. You need this condition. In the book, you can find an example of a function which is not 2π periodic, where if you do this, you get some garbage. You get something that doesn't even converge. Okay, so okay. So in the book, I mean, unfortunately, I can't really explain to you why all this is happening because it actually requires quite a bit more analysis. But in the book, you can find an example where you have if you try to pull this off with a non-periodic function, if you just differentiate every term, you just get some garbage. Okay.
mm-hmm. But for non-periodic function, can I get FSF without?
Yeah. So for non-periodic function, you can compute the Fourier series for sure, but you may not be able to differentiate.
Mm-hmm. Got it.
Right. In general, if you differentiate a series, that changes the terms, right? And there's no reason in general that should converge after you differentiate it. So this is true, and Fs of f prime converges for all.
Professor?
Yep.
So I think you said something about, well, if you try to pull take the derivative of the Fourier series for a non-periodic function, you get garbage. I think you said that, correct?
You may get garbage. You may
get garbage.
By garbage I mean something that doesn't converge. For example, exercise. Differentiate this term by term.
Oh, I tried it and it looks like garbage.
Yeah, it doesn't converge.
I thought it would produce a delta Dirac function, but
yeah, so delta Dirac function is not a function, right? So
okay.
There's a way of making sense of what it produces, but that's beyond the scope of this course. You're right. There's a way of defining something more general than a function so that all of this always works, but we won't be doing that. I mean, if you're a physics major, you probably already did that because it's called a delta Dirac function. Anyway. Okay. So that's the second example I wanted to present. So now I want to show you I basically want to show you some more demos of what this really means, because I think it's really cool and everybody should have a feeling of what it means. So let me show you some applications, unless there are more questions. Okay. So let's look at some applications. So first, I'll show you a mathematical application. So here's a mathematical application. What's the following sum? 1 plus 1 over 3 squared plus 1 over 5 squared plus 1 over number theoretic series. 1 over 7 squared plus dot dot dot. What is that equal to? Okay, it's a hard problem. So this is the problem. Okay, somebody already got the answer. Pi over 4, right? That's not exactly right. Close. How would you sum this series? So questions like this were open for several hundred years, actually. Like people had all these simple series to write down that they had no idea how to find them. And then after Fourier series was developed, it turned out you could solve many of these questions very easily. And still, Fourier analysis is one of the main tools in number theory. So the answer to this is actually written here. What happens if you plug in 0 into this identity? Right? So let's remember what's written here, right? So we know x is equal to pi over 2 minus, forget the constant here, 4 over pi, yeah. Squared. This is an honest to God thing that's true for all x in minus pi to pi. So what x should I plug in? Zero. Just plug in 0. 0 equals pi over 2 minus 4 over pi. And lo and behold, 1 plus 1 over 3 squared plus 1 over 5 squared. So that implies that the series actually equals pi squared over 8. Okay. So this is like a really deep thing. Because it's not easy to find these sums of these series. There's still things like this that are open. But one of the heaviest tools we have is Fourier analysis. Okay, so somehow this orthonormal basis of cosines and sines turns out to also be related to number theory. Okay, here's another cool application. So okay, so this is a guitar, right? And I'm just going to play a chord. I don't know if you can see it. Does anybody know what chord this is? I don't know how good the sound quality is. Yeah, G major. Good. Okay. People are better at music than I am. So as you probably know, G major is actually like you play a bunch of notes together or one after another, right? So the notes are like G, B, what are the notes? D, no, yeah, G, B, D, G, B, G. Okay, is that correct? I'm actually just learning how to play guitar now, so I'm kind of primitive in this. But see, where does the chat go? Okay. So the way you should really think about what Fourier series does is, you know, a chord is a sum of notes, right? And what a Fourier series does is it can do this for any sound. right? So you can decompose any sound into a sum of pure tones, okay? And that's really what this formula is saying, right? That suppose you have a periodic function, right? Then the Fourier convergence theorem is telling you that this is true, right? And that really is the same thing, right? It's decomposing a complicated sound into some very simple sounds that are cosines and sines. So actually, there's a cool simulator online which allows you to play with this. So I've never tried sharing sound on Zoom, but let's try it. Okay, so I'll send you a link to this. So that's a sine wave. And you can play it. So can people hear that? I mean, it's not a very nice sound, I guess, but okay. Wait, where does the chat window go?
Yeah, we can hear it.
Okay, good. So now on this app, what you can do is you can have, some other sound like square wave. That's the example one we looked at. And now, so square wave sounds like this. Okay, it's not a great sound. It's different from sine though. And what the Fourier series allows you to do is to approximate the sound by sines and cosines, right? So as you increase the number of terms, first you have a sine, now you have 2 terms, but remember the even ones are missing. Now you have the odd one. Cosines are 0, right? Because it's odd function. Even ones are missing. You can play with this if you want, but this is what it really means. I'm sorry, that was probably highly unpleasant. Okay. But yeah, that's kind of what Fourier series means. And I mean, there's actually this whole area of math is called harmonic analysis. Okay. And let me briefly mention one more application, which is probably quite relevant, even if you haven't thought of it this way. Yeah, I don't know where my chat window went. Okay. The third application is MP3. I don't know if music is still stored in MP3s, is it? Oh, the cat jumped. Oh, interesting. Oops.
Oh, by the way, like for example, you want to compress a sound, you just basically like store the information about like n is greater or n is lower, and you drop out the rest.
Yeah, exactly. That's what I'm about to say. So what is MP3? It's an audio compression format. I'm not sure what exactly has happened to my writing, but anyway. So suppose you have a song. What's a song? Well, a song is actually just a function. Okay, it doesn't look like a function anymore, but it's a, okay, that definitely doesn't look like a function. A song is just some wave pattern on some interval. So it's like some function from maybe not R to R, but from some set of R to R. So what do you do? Well, you break it into chunks of length 2 pi. Why not? or any other number, right? We discussed that you could do that. And now you have a bunch of little functions, f1, f2, f3, f4, f5. And for each one, just take its Fourier series. So you have some, you know, whatever. You have some a0 over 2 plus okay, so do it for each one. So now you have, I guess I should give these names. So you have the first Fourier coefficients, and you have the Fourier coefficients of the second one, the Fourier coefficients of the third one, and so on. The one interesting property of Fourier coefficients that we already saw in the examples, going back here, is that these terms are going down pretty fast, right? In the first one, they're going down like 1 over n roughly. In the second one, they're going down like 1 over n squared. Right? So you can prove this. We won't prove it in this class. But for any reasonable signal, the terms decay rapidly. And so the idea is, well, just keep up, I don't know, some small number, 50, for your coefficients for each chunk. Okay, so you're throwing away information, right? Here you have infinitely many Fourier coefficients. And the compression scheme is just keep the top few. This is like, musically speaking, it's like you're throwing away like some of the overtones, like some of the, you know, way out there overtones. And that's basically what MP3 is based on. I mean, okay, there's more, but this is one of the key things that audio compression is based on, right? So keeping the top Fourier coefficients leads to compression. And yeah, okay, so that's the last application I wanted to say. Okay, so that's, oh, whoops. Okay, so there's this thing called section 10.4. I guess forgot to say about, which is actually very straightforward. And it answers the question, what if you only want sines? Okay, so suppose you're given function f now from the interval 0 pi to r, satisfying f of 0 equals 0. So let's say you're given a function. So this is the interval minus pi to pi. And you have some function that just looks like this, right? So f just lives here. Well, how can you use Fourier series? I mean, this is another thing that comes up in applications. Well, one sort of easy thing you can do is you can extend this to an odd function in the obvious way. So what can you do? Well, you can just, right now the function's only defined on half the interval. You can define it on the other half to be whatever it would need to be to make the function odd. So you define f odd from the full interval f of minus x equals minus f. Right? And then you take the Fourier series, you get that f odd of x well, now what's the point, right? It's odd. So there are no an coefficients. So it's just going to be a pure sine. Right? Because it's odd. Okay, but now this is also, this is on the whole interval. But then that implies that f of x itself is equal to this on the half interval. Okay, so it's like a cheap, easy trick. But this is something that comes up. This is called an odd extension. Similarly, you can do an even extension. And the difference now is that you're computing the Fourier coefficients of the extension, right? Not of the function. The Fourier coefficients of the extension these give you the coefficients in the sine series for the original function. Similarly, you can do the same thing to express the sum of cosine. So there are a few homework problems here that you can do. Okay, so this is like not a deep thing, it's just a little embellishment. Okay, I said I was going to cover differential equations. Okay, so let me just go a couple of minutes over and give you a one-slide summary of differential equations. So in differential equations, what did we do? We roughly had two kinds of equations, right? We had, well, okay, let me not draw this whole line. Okay, so first we had systems of second order equations. Yes, you will have lots of practice finals on B courses. Yes, I'll send a detailed email about practice finals. And we conceptualize this as a linear transformation between some function space from some function space itself, where, oops. Okay, I'm not sure what's going on with my. Okay. Okay, this is really weird. It's barely legible, but okay. And the other kind of equation we had was a system of first order ODE, in which we had, d by dt of x of t equals ax, t, where A is an n by n matrix. And we thought of this as being a linear transformation from Fn to Fn by t equals d by dt minus A. Okay. So in both cases, there was an equation, there was a linear transformation, linear operator on some vector space. We had three questions about first, and we found that this is the kernel of the C, the homogeneous solution, which was a span of some exponentials. Okay. Okay, somehow this, oh, okay, good. Or, or span of some cosine, exponential times cosine. And the answer to which one it was depended on the roots of the auxiliary equation, which gave you factorization of t into first order differential operators. Now, what was the parallel in the second in the other setting? Well, the parallel, which is quite actually related, for the homogeneous general solution, we had that, well, the kernel of T was again a span of some exponentials. If A is diagonalizable, and okay, may have to use the real and imaginary parts if lambda is complex, right? And you can see the parallel here, right? What are the eigenvalues? Well, the eigenvalues are roots of the characteristic polynomial, right? So in both cases, the general solution was spanned by some functions which were exponentials, and which exponentials they were came from looking at roots of some equation, which in the first case was the auxiliary polynomial, the second case was the characteristic polynomial. And these things are actually connected, right? We saw that there was a connection between these two things, which I'll just draw here. If you take the matrix A to be, I believe 0, 1 minus C over A minus B over A, and apply the linearization trick, you get the same answer using both these methods. So these are actually, in some sense, they're all just different manifestations of the same method. Okay, the second step was how do you find the inhomogeneous general solution? So, well, if you want to solve T of y equals some function f, where f is a polynomial, then you consider an ansatz, you consider the restriction of this thing to a space of polynomials, and you solve the matrix version for some basis. Right? This was the method of undetermined coefficients. And here, this was exactly the same. So this was to find like a particular solution, right? YP, let's call it. And again, if this is now each entry is a polynomial, then consider P going from Pmn to Pmn and solve the difference is this is a second order ODE with constant coefficients. This is a system of first order ODE. Okay, so these are, the left column is the first two lectures on differential equations, the right column is the second two lectures on differential equations. Okay, and then in both these cases, after you do that, you get that the general solution is the homogeneous solution plus the particular solution. Okay, so it's really the same idea. And the last step is the initial value problem. Well, to do this, you have to solve a little linear system. Oops. And this is invertible because this map from the homogeneous solutions to R2, the evaluation map essentially, right? taking y to this vector is an isomorphism. Okay, this is what's called the Wronskian lemma. And again, the third step here is pretty much the same. You have to solve this, you have to find an element in the kernel of T, or you have to find some function within the general solution that matches the initial data. And here again, you have to, I mean, okay, I guess you have here yp of 0, yp prime of 0. And here again, you have to solve a system like this. And again, this is invertible because the evaluation map from the solution to the differential equation to Rn is invertible, is isomorphism. Same thing. Okay, so really there are very few ideas in this. There seems like there are a lot of little different versions of it, of the same ideas, but really the left and right side are based on similar ideas. And this is why this is included in this course, because pretty much everything we did in the course in linear algebra, except SVD, is used somewhere in this page, right? Like basis, eigenvectors, you know, linear transformations, composition of linear transformations, solutions to homogeneous, inhomogeneous linear systems, like different notions of linear dependence, like abstract vector spaces, everything is used. So this is actually a good, one good exercise is go through this whole slide and identify what linear algebra concepts are used in every step. Okay. Oh yeah, somebody asked, do you need to know this for the exam? Okay, this is not on the exam, but it was on the homework. Thank you. I said this is not going to be on the exam, and it's not. It's optional, but it's kind of the same thing anyway. So a good exercise is, maybe I'll end with this exercise. Identify which linear algebra concepts are used in every step in the previous one. Okay, so that's it. There will be practice exams posted. And details about the final exam will be emailed to you. Everybody will get all their homeworks and quizzes graded by Monday. So you will have all the data you need to decide whether you want to grade or not. And I will send detailed information with it. But yeah, that's it. So thanks a lot for the course.
Thank you, Professor.
Thank you.
Thank you.
Professor.
Thank you.
Thank you.
Thank you.
Thank you.